Hi there. This video series is to display my problem solving and learning abilities. I plan to show that I can solve any programming problem, regardless of whether I already have expertise in a particular language. I hope this helps others in my field to learn not just how to solve a particular problem, but how to teach themselves a solution to an unfamiliar problem. Currently, I am learning Python. I have no professional experience in the language and have only been learning it since mid-January. My only formal training is completing the Python for Programmers course on Execute Program. While I'm picking Python up fairly quickly, I cannot claim any real expertise. Today, I'm showing my approach to solving the 21st Project Euler problem from start to finish, vocalizing my thought process throughout. As always, I will link to both Project Euler and my repository in the description. Let's dive in. Alright, let d of n be defined as the sum of proper divisors of n, numbers less than n, which divide evenly into n. If d of a equals b and d of b equals a, where a does not equal b, then a and b are an amicable pair, and each of a and b are called amicable numbers. For example, the proper divisors of 2020 are this list, and therefore d of 2020 equals 284. The proper divisors of 284 are this list, so d of 284 equals 2020. So those are two of the amicable numbers, and they want us to evaluate the sum of all the amicable numbers under 10,000. Okay, so we pull up our code. And as per usual, we start by pulling my little date time thing in so that we know how long the code took to run. Okay, so obviously we need to do some form of a loop. And what I think that I want to do is have a dictionary where I store a number to a list. Well, that doesn't tell us the amicable numbers, does it? What I was thinking was store the results of d equals 284, but that doesn't really help necessarily. So we need to, let's see. Proper divisors. So this is going to do some of the things that we've done before, where we find the divisors of numbers. And let's see. So the sum of the divisors, that's our trick, really. The sum of the divisors, if that is under 10,000, then it is an amicable number. So, like, for instance, we start with 1, we're going through to under 10,000, or we're going through to 9,999. We get to 220, we find the sum of the proper divisors, we find that it is 284. 284 is under 10,000 also, which means that it could be an amicable number. Okay, so it's not just whether that number is under 10,000, but we're going to have to collect a list of these numbers, I think. So basically, we get to 220, and we store it in a dictionary where it's like 220 is the key and 284 is the value. We get to 284, we find that sum to be 220, we look in our dictionary, check 220, see if it is equal to 284, which it will be. Okay, so we want I'm just gonna call it num2 divisor sum. And this is going to be an empty dictionary at first. And then, okay, so a proper divisor, number less than n, which divide evenly into n. So 1 cannot have a proper divisor. So we're going to say for n in range, starting with 2, going up to limit and we're going to do limit equals 1,000. Don't need semicolons. I've been doing a little bit of Java. And it breaks my memory for Python. And then some amicables equals 0. And what we want to do is find sum of divisors. Def for a given num. And then for f in range 2 square root of the number is 1. And I'm gonna have to end this. If no parentheses necessary, num mod f equals 0, then sum plus equals f, and sum plus equals num divided by f, which we might have to do this. So that gives us both the factor and the other side. So like going back to this 220, when we divide by 2, we get 110. We add both of those at the same time because why would we check every number when we don't need to? We could make this somewhat more efficient, for sure, and we might have to. I know that in previous problems we've created more efficient algorithms for these things. But I think that for this, we do not need to. But we'll see. We're gonna find out, aren't we? So for n in range, we want to find the divisor sum equals find sum of divisors for n. Obviously, we are not testing this right now. But I think it's also not very complex code yet. We'll see. Let's see. So if we find the divisor sum, it's actually num to divisor sum of n equals divisor sum. And then we're going to do if num to divisor sum of divisor sum equals n. And once again, I'm adding parentheses unnecessarily. Then some amicables plus, or yeah, let's just do plus equals, or just do equals plus n plus divisor sum. I believe this will actually throw an error. We don't want that. We want to do like a get where we pass divisor sum, and let's default it to 0 because 0 will never equal n. And let me think through this here. That's it. That's the whole algorithm. Then I'm just going to print some amicables, and we're going to see, does this work? That would be weird if it worked on literally the exact first try. Okay. Oh. Well, that's fair. I'm probably gonna have to log in again. Oh, maybe not. Nope. Okay. Let's, instead of doing a bunch of other stuff, let's add a print here. Now, I'm going to guess that what happened here, just to try to think it through. So, amicable numbers gotta come in pairs, right? Because you're not going to get a number is only one value. It can't be more than one value. So I was thinking maybe there's some numbers that have more than one amicable number, but that can't really be true. It has to be a pair. So this should work, but it looks like obviously it isn't. So let's see. Ooh. Well, hold on. Because look at this, 6 and 6, 28 and 28, 496 and 496. That's where our errors are. I just want to point out that this, like a 1/10 of a second, not even 400th of a second, for that one. And then the second run, whoops, which had printing out all of these extra pairs. Oh goodness. Let's see. 30.481, 30.53, so a tiny bit longer. And then this one, similarly, like 500ths of a second is how long that took. Okay, so there's the 284 and the 220, and then these numbers are also distinct, as are these, and these, and these. So, this number probably is right, I would say. There we go. Obviously, like, we don't necessarily need this print. I'm going to make the decision for once to leave this in here, just because it was so useful, but it also is not necessary. And yeah, let's see. So all we did is, for every number from 2 to the limit, because we know that the number 1 is never going to be an amicable number. We also know that for like 2 and 3 and 4, but that's, this way we're letting the program tell us instead of going to the first amicable number. Storing all of these isn't, strictly speaking, necessary. I'm going to add some white space to make this a tiny bit more readable. So this part has an O of n, obviously, and then this part has an O of the square root of n, so it's n times square root of n, effectively. So what are we doing here? So for every number starting at 2 up to the limit, so because it's Python, then the range method does not include this limit. The stop is never inclusive, it's always exclusive, so it'll stop at the one before. For every n in this range, we find the sum of the divisors, and then we see whether that divisor sum is in our dictionary. If it isn't, we return 0 using the .get. We could do this a different way, but this way we get a one-line little nicety. And if it is there, then, and it equals n, then we add it to the sum. And in this case, we're also printing out, like, hey, we found this. And then we set the num to divisor sum in the dictionary to prevent that bug that we found where we were finding that these two numbers were equal. We also could have, like, been like, if divisor sum equals n, then, or does not equal n, and the other condition. But I think that just adding it after we do the check makes the most sense. Because that way we know it's not already there. And then, as I said, this finds sum of divisors. This is a really, really simplistic method that we could make slightly more efficient, like by well, no, because they're not looking for prime factors, just divisors. So maybe this is the most efficient way. Let's see if they have a little document for this one. They do. This is the repetition of the problem. There is a possible ambiguity here. Should both members of a pair be below 10,000, or does the condition also include pairs A, B, for which A less than 10,000 but B not? If you displayed all pairs you found, you will have noticed that there is no such pair, so we will not bother. Second issue is there exist so-called perfect numbers so that D of A equals A, like we saw the number 6. Problem statement says that is not an amicable pair. First, suppose we have a function sum of proper divisors, which is the function that we wrote. How can we use this efficiently? Let us concentrate on that first. Suppose one has coded for A equals 2 to... Oh, geez. That seems very inefficient. So they're basically going through all of these numbers, and then if A does not equal B, then we check whether the sum of proper divisors A equals B, and if sum of proper divisors B equals A. So then it's like, it's doing it this many times, which is, you can see, it's a pretty big number. And then they're showing that you could cut it literally only in half. If we calculate this, so our main program now becomes sum equals 0 for A equals 2 to 9999, B equals sum of proper divisors A. If B greater than A, then we check the sum of proper divisors for B, blah blah blah, that. So this is pretty similar to what we have done, except then it goes out and calculates for B, even though we will get to B again later. Even if for all A sum of proper divisors A were greater than A, we would invoke our function only this many times and almost 5,000 times speed increase. Let us now concentrate on the function sum of proper divisors. So the way that I did it actually does has an inefficiency in that there is this dictionary. If you were concerned about the amount of space and memory being used by this algorithm, this would not work. But as I've said before, I just have lots of memory space, so I don't worry about those things. And obviously as this number gets larger, things will slow down. Like, even if we go to 100,000, let's see, 2938, 2937. So it took a little over a second, or yeah, just a teeny bit over a second for that. 37.64 to 38.69. And obviously as this gets bigger, the speed is going to increase and increase and increase. But I think this is still a pretty efficient algorithm. And then it talks about the sum of proper divisors question. Very naive version is just look for the factors. Except for one, they come in nice pairs so that their product is 36. When we found one of the two, in fact, we know the other. Okay, so I avoided that by just starting at 1. Because 1 is a factor of literally all whole numbers. And then it talks about the square root again. To find all pairs, we need only to check up on square root of n. Odd numbers cannot have even numbers as divisors. The converse is not true. Even numbers can have odd divisors. So they're doing 2 increases in efficiency. We only did the one where we only went up to the square root. And actually, for numbers under 10,000, it might be the case that it must be the case that there are no amicable numbers with a square root, because we're actually counting the square root twice here. Let's add a little bit of a statement here. If f, let's say f not equal to int, or actually, basically I'm saying only add that the result if it's like not literally the same as f. So add in just doubling the computation for this. It might be better to pull this out into a variable, but not a super big deal. That just prevents us from, like, for the case of 36, adding 6 twice, which I'm pretty sure we would have been doing before. So then the other improvement is just for odd numbers, just step up by 2 instead of just by 1. So that's another efficiency improvement that we could make, speed us up a little bit. If we know the prime factorization of n, it is equally to calculate the sum of the divisors of n from that. Sum of the proper divisors of n is then the sum of the divisors of n minus n itself. More on this can be found on this companion website, which I clicked on by accident. Okay, so note the line while p times p less than or equal to n and n greater than 1 prevents us from checking prime factors greater than square root of n. If n greater than 1, then sum equals. Covers the case that one prime factor greater than square root of n remains. Okay. So, just talking about how when you make it this efficient, the code becomes a little bit more complex and a little bit more confusing, I think. I personally am pretty happy with this solution. Obviously, as we said, it can be slightly more efficient by the odd numbers thing. And then there's another improvement that could be made using prime factorization. But I think that our version is pretty good as it stands. Obviously, it can also work for 100,000. I'm not sure I want to run it for 1,000,000, but I'd say that this is a pretty good solution for the problem statement that is in front of us. And with that, I'll catch you in the next one.